Okay, let's unpack this. Imagine the most complex, capable AI model. Maybe it writes code, translates languages, or generates stunning images.
Hmm.
Now, picture something incredibly fundamental to its operation, like how it decides where to put its attention. What if I told you that its core ability to understand complex patterns, or its theoretical limits on what it can understand, could fundamentally hinge on something as seemingly minor as how it breaks a tie?
Yeah, not a necktie, right? A mathematical tie.
Exactly, a tie and its internal calculations.
It sounds almost, well, absurdly simple, doesn't it? But this isn't just a hypothetical.
No.
No, it's a surprising finding from some really cutting edge research. How these models handle that specific scenario where multiple parts of the input seem equally important at a given step turns out to be profoundly significant for their underlying capabilities.
And that's exactly what we're diving deep into today. We've been sifting through a fascinating new paper from researchers at ETH Zurich. It's titled Unique Hard Attention, A Tale of Two Sides.
Right, and it's a proper deep dive connecting modern machine learning ideas all the way back to, decades of work in formal language theory and logic.
We've got the paper itself, some detailed notes, and even a bit of a timeline tracing this specific research thread back a few years.
And our mission really is to go beyond the technical jargon in the paper. We want to pull out the most important nuggets for you.
Show you why this subtle point about tie breaking actually matters so much.
Yeah, what it reveals about the fundamental limits of these powerful models and where this specific academic innovation fits into the bigger picture of understanding AI.
Okay, so let's set the scene. Basics first. Most of the powerful AI models we hear about today are built on the transformer architecture.
Right.
And the engine driving that architecture is the attention mechanism.
Exactly. Attention is essentially the model's way of looking at a sequence of input, like words in a sentence, and deciding which parts are most relevant for understanding or predicting the next part. It assigns scores, weights to different input positions.
Higher scores for more important stuff at that moment.
Precisely. Now, the standard transformer uses what's called soft attention. It calculates these scores and then uses a function, usually softmax, to turn them into a probability distribution.
Meaning it pays some attention to many parts of the input simultaneously, just with different strengths.
Correct. But for theoretical analysis, researchers often like to simplify things, so they look at hard attention.
Hard attention.
Where the model selects just one single position to focus on, and even more specifically, unique hard attention, or UA.
Aye, got it.
Which picks the single position that received the absolute maximum attention score.
Okay, so hard attention picks one, UHA picks the best one. But what happens if, two or three positions all tie for that maximum score?
That is precisely where this paper focuses. With UHA, you must pick only one. So if there's a tie, you need a deterministic rule to break it.
A tiebreaker rule.
Exactly. And the paper zeroes in on two specific rules. Leftmost-hard attention, which always picks the tying position furthest to the left in the sequence.
Okay.
And rightmost-hard attention, which picks the one furthest to the right.
Leftmost or rightmost? Seems straightforward enough.
You'd think, but here's the paper's core finding, the really surprising point that anchors this whole study. This seemingly tiny choice, left or right tie-breaking, markedly impacts the model's expressivity.
Markedly impacts. Wow.
Yeah, they even call it, and I love this quote from the abstract, a wonderful fact to reflect upon, that leftmost and rightmost unique hard attention are constituted to be profoundly distinct.
Profoundly distinct, just based on how you break a tie. That's kind of wild.
It does seem counterintuitive. Now, it's important to frame this. The researchers are looking at what they called a bare-bone idealization of the transformer. Meaning they're modeling it with finite precision, like real computers have, but they deliberately remove complexities. Things like positional encodings, which normally tell the model where tokens are in the sequence.
Okay, no positional info.
And they use strict feature masking. That means a token at a certain position can only look at things that came strictly before it, not itself, not things after.
And why do they simplify it like that? Why strip those things away?
To isolate the effect they want to study. By removing other factors that could influence the outcome, they can rigorously, precisely analyze the exact expressive power of the UHA mechanism itself, specifically under these different tie-breaking rules.
Right. It's like studying a simple lever to understand mechanical advantage before tackling a whole complex machine.
Exactly. It lets them get at the fundamental principle.
Okay, so let's get into the academic innovation here. The paper isn't just saying, hey, these are different. They're proving it rigorously. The first big innovation is showing how left and right attention end up with fundamentally different capabilities.
Yes, and they use an interesting tool for this, an intermediary theoretical language called BRASP. It sort of helps bridge the gap between the abstract transformer operations and formal logic.
B-RASP. Okay. And what's the key intuition there?
The key intuition is that rightmost attention can perform certain fundamental sequence operations that leftmost attention it struggles to replicate reliably.
Can you give an example from the paper? What can rightmost do that leftmost finds tricky?
A key example they use is the ability to read the value of the input position immediately to the left of the current position. Let's call the current position T, so we're talking about position T1.
Okay, the thing that just happened.
Right. A rightmost attention mechanism, if you set up the scores correctly, can target and select position T1 quite efficiently.
Because T1 would naturally be the rightmost position among all the positions to its left, TT?
Exactly. If it has the max score among those, the rightmost rule picks it. But a leftmost attention mechanism, it has trouble with this specific task.
Why?
Because to reliably pick T1 using the leftmost rule, T1 would have to be the only position to the left with the maximum score. You generally can't guarantee that some other position, maybe way further back to the left, say TT1, won't also happen to have the same maximum attention score.
Ah, and if that happens?
If that happens, the leftmost rule forces the model to pick that earlier position, T instead of the immediately preceding one, T1.
I see. So leftmost attention inherently struggles to reliably target the most recent thing in the past if there are identical scores further back? That makes sense.
Precisely. And this difference in capability leads directly to their first major formal result, which is a core academic contribution of the paper. They prove that leftmost U-hats with future masking are strictly less expressive than rightmost U-hats under this idealization.
Strictly less expressive. So it's not just a different flavor, it's actually weaker.
Yes. It proves a fundamental separation in power where maybe intuitively you might have assumed they'd be equivalent, just mirror images.
Okay, so innovation one, proving leftmost is weaker. What's the second piece of academic innovation?
Well, they don't just say it's weaker. They figure out exactly how weak it is. They pinpoint its expressive power by showing it's equivalent to some specific, well-understood formalisms from, decades of theoretical computer science.
Right, this is where the connection to that older work in formal languages and logic really comes in.
Exactly. They show that these leftmost UCATs, under their idealized settings they call the model class TF, are equivalent to several established theoretical models. The most significant one for understanding its capabilities is Linear Temporal Logic, LTL.
LTL, temporal logic. Okay, that sounds pretty abstract. What does that mean in terms of what the model can actually do?
Think of temporal logic as a language for describing patterns over time or along a sequence. The specific fragment they find TFA equivalent to is called LTL.
LTL with existential minus. What's the minus mean?
The key part is that ed, which basically means it only includes the past existential operator.
Past existential operator. Okay, break that down.
In simple terms, it means the logic can check if a certain property or symbol existed at some point in the past relative to the current position.
Like, did the symbol A appear anywhere before the current word?
Exactly. Or was the value greater than 5 at any point earlier in the sequence? It can verify the presence of something somewhere in the past.
Okay, so it can confirm if something happened before now. What can't that kind of logic do? That seems like the crucial part.
And this is where the limitation bites and where the academic significance lies. LTLA fundamentally cannot express more complex temporal relationships.
So as?
Crucially, it can't express things like checking if something was the most recent occurrence of a pattern. Remember our T1 problem? Right. Or checking if a condition held continuously until a certain point. That inability to reliably pinpoint the latest relevant event in the past is a key restriction baked into LTLism.
So the model can tell you if you saw a right command before, but not necessarily which one was the last one.
Precisely. And the paper formally proves this equivalence. TF is equivalent to LTL and also to other formalisms like a type of automaton called partially ordered finite state automata, or PAFAs.
And nailing down that equivalence, that's the second big innovation, providing the exact mathematical boundaries.
Exactly. It tells us precisely what logical patterns this idealized leftmost model can recognize, and more importantly, what it cannot. It's not just weaker. They've defined how it's weaker in a very formal way.
And how does this compare to previous work? Did people already know this?
Well, they contrasted explicitly. Earlier work, like from Yang and others in 2024, had shown that a similar U-hat model, but one that was allowed to use either leftmost or rightmost tie-breaking, was actually equivalent to full LTL.
Full LTL.
Yeah, which does include operators like since and until. Those are exactly the kinds of operators you need to talk about the most recent past event, or things holding true over intervals.
So the key insight here is that being forced to use only leftmost attention is what causes the drop in expressive power, down to that weaker LTL fragment.
Exactly. The constraint makes all the difference.
Okay, so we have this very precise, very academic understanding of the limits of leftmost UHA. Now let's connect the dots. Why should someone listening care about the theoretical limits of this idealized model? How does this hit the real world of AI?
Right, because here's where another crucial equivalence comes into play, building on this paper's results and other recent work, specifically mentioning Li and Cotterell from potentially 2025.
Okay.
Under the specific idealizations used in this study, finite precision, no positional codings, future masking, it turns out that leftmost UHA is theoretically equivalent to standard soft attention transformers.
Whoa, hang on. The standard soft attention, the kind that's actually in GPT, Claude, all the big language models we use.
Yes.
That soft attention is, in terms of its fundamental expressive power under these idealized conditions, equivalent to this simpler, weaker, leftmost hard attention model.
That's the implication, yes, within the scope of this idealization. And this is a really, really significant insight.
Why it's significant?
Because it suggests that leftmost UHA isn't just some abstract theoretical curiosity. It acts as a principled abstraction for understanding the fundamental, inherent expressive limits of standard soft attention transformers themselves.
And that equivalence helps explain some things we actually observe, like limitations in real-world models.
Exactly. The paper makes this connection explicitly. They point to tasks where standard transformers have been shown empirically to struggle. One example is the flip-flop language task.
Flip-flop language, what's that?
It was studied by Liu and others in 2023. Basically, the model processes a sequence of instructions like write X and read. When it sees read, it needs to output the value from the most recent preceding write instruction.
Okay, so if the input is write A, write B, write C, read, the output should be C.
Correct.
And if it's write A, read, write B, read, the output should be A first, then B.
Exactly. It requires reliably locating the value from the last write command in the history.
And soft attention struggles with this.
Empirically, yes. And this paper suggests why. Because soft attention, like its theoretical equivalent leftmost UHA, lacks the ability to locate the most recent rightmost write instruction.
Because of that LTL limitation, it can only say, did a write happen sometime in the past?
Exactly. It can't easily express which write happened, such that no other write happened since then. You need something like the LTL since operator for that, which LTL and thus leftmost UA and idealized soft attention don't have.
So this theoretical work provides a potential explanation for an observed empirical difficulty. It's not just that the models aren't trained well enough. It might be a fundamental architectural limit.
It provides a strong theoretical backing for that possibility, yeah. Under this idealized view, it points to an inherent limitation.
What about things that do seem to help models deal with recency, like positional encodings or techniques like alibi? Alibi biases attention towards recent tokens, right?
Right, and the paper offers some speculation on that too. They suggest that the empirical success of techniques like alibi might be partly explained because they are helping soft attention models approximate the behavior of rightmost tie-breaking.
Ah, because rightmost can handle recency better.
Exactly. Remember, rightmost UHA is more expressive and better equipped to find the most recent position with the max score. So alibi might be like a practical patch that nudges soft attention closer to that more powerful rightmost behavior.
Okay, let's try to summarize the capabilities then. Based on this LTL equivalence for leftmost UHA and by extension for idealized soft attention, what can these models definitely not do well, theoretically?
Okay, so based on being equivalent to LTL, they cannot reliably handle tasks that require checking for strictly continuous patterns, which falls under locally testable languages.
Like seeing ABC in a row.
Right. They also struggle with recognizing languages with nested structures, like correctly matched parentheses. That's the classic bounded Dyke languages example.
Okay, no complex nesting.
And they can't handle tasks requiring even simple counting, like determining if there's an odd or even number of a specific symbol. That's the parity language, which is known to be nonsense-free, putting it beyond LTL's capabilities.
Why can't they do these? Because LTL just isn't powerful enough.
Essentially, yes. LTL is fundamentally limited to checking for simple existence of something somewhere in the past. These other tasks require more sophisticated logic, like counting or reasoning about intervals using operators like until or since, or the structure of automata needed for nesting.
Okay, so that's what they can't do. What can they do reliably, according to this theory?
Well, they can handle simpler tasks, things like checking if a specific symbol or maybe a simple pattern exists anywhere in the history up to the current point.
So did error appear anywhere in the log file so far?
Yes, that kind of check. Or recognizing patterns that depend only on the over a prefix of the sequence seen so far, not on intricate local or temporal relationships within it.
The paper also mentions something about duality, a symmetry.
Ah, yes. There's a neat theoretical symmetry. If you flip the setup, if you use past masking, meaning attention can only look at tokens after the current one.
Looking into the future instead of the past.
Right. And you combine that with rightmost UHA tie breaking, that configuration, which they call TP-US, is theoretically dual to the future mask leftmost UFI we've been discussing.
And what's it equivalent to?
It turns out to be equivalent to LTL plus, which is the fragment of LTL with only the future existential operator. Will something happen at some point in the future? It shows a nice balanced theoretical landscape depending on the direction of masking and the tie-breaking rule.
That is neat. But we need to remember the caveats here. The paper itself point out limitations.
Absolutely. It's crucial to keep perspective. This is a purely theoretical result. It applies to a specific, highly idealized model, finite precision, strict hard attention with only one tie-breaking rule allowed, and crucially, no positional encodings.
So it's a controlled lab environment for theory.
Exactly. It doesn't directly address all the complexities of real-world models, things like how they actually learn during training, the dynamics of that process, or how multiple layers interacting, residual connections, and positional encodings change the practical picture.
But still, the theoretical insights, especially nailing down the expressive power of leftmost UHA and showing its connection to soft attention, that seems incredibly valuable.
Oh, definitely. They provide a fundamental theoretical grounding. It helps us understand why even these incredibly powerful soft attention models might have certain inherent architectural limitations when it comes to handling specific kinds of logical or temporal patterns. It suggests it might not just be about scale or data.
Right. It potentially points to limits baked into the architecture itself, at least in this idealized view.
It's a significant step in mapping the theoretical boundaries of these systems we rely on more and more.
So wrapping this deep dive up, the key takeaway really is that a tiny implementation detail, how a transformer breaks a tie when multiple inputs seem equally important, has this profound, mathematically provable impact on what it can fundamentally express or understand.
Yeah, that's the core surprise.
And the specific academic innovation highlighted in this ETH Zurich paper is providing that precise theoretical characterization of the weaker leftmost attention variant, showing its equivalent to that LTL fragment.
And then connecting that limitation to standard soft attention under idealization.
Which in turn helps explain some observed struggles of real-world models, like that difficulty with finding the most recent past event.
It brings a new, sharper level of theoretical clarity to the capabilities and potential limitations of the models powering so much of today's AI.
Okay, building on all that, here's a final provocative thought for you, our listener, to consider. Given that something seemingly so basic, like reliably locating the most recent piece of relevant information, appears to bump up against a theoretical limit related to temporal logic expressivity, lacking that sins operator. What might this imply about the kinds of complex reasoning or pattern recognition that could remain inherently challenging for transformer architectures, no matter how massive they become or how much data we feed them?
Yeah, does truly sophisticated understanding of complex temporal sequences, or maybe certain kinds of structured reasoning, necessarily require computational mechanisms that go beyond the fundamental expressive power captured by formalisms like LTL?
Something to mull over. Where do the boundaries really lie?